Hi, my name is John Gulbranson and I'm the president of International Test Instruments. In this presentation I will talk about the history of PC buses from ISA to PCI Express. So it all started back in 1981 when IBM created the original IBM PC. That machine used a Intel 8088 CPU running at 4.77 megahertz, which resulted in the blazingly fast I/O bandwidth of 4 megabytes per second. The ISA standard, however, was created a few years later in 1984 when the PC-80, the improved PC, was created, which used the 8286 CPU. And that CPU uses a 16-bit data bus running at 8 megahertz for a total memory and I/O card bandwidth of 16 megabytes per second. There are two versions of the ISA card. The original 8-bit, which was used for the 8088 or original IBM PC. And you also have the 16-bit extended cards from the PC-80, which is technically only the ISA bus. The original one is not technically part of the ISA standard. Only the 16-bit one is actually spelled out in the standard, but commonly we call both of those card versions the ISA card. So depending on the actual CPU used, the 8088 or the 286, you can address either 1 meg or 16 meg of address range on the CPU bus and therefore also on the I/O card. Both of these CPUs support 64K of address space. One of the problems, of course, is that the ISA bus is not very fast. It was an old design from 1980, essentially, and after about 10 years, when Windows came along and other GUI-based operating systems, the I/O bandwidth was not enough to support the advanced graphics cards that started to come along. So the graphic cards manufacturers came together, and through their group, the VESA group, Video Electronic Standards Association, created a VL bus or VESA local bus, which essentially was again a direct attachment of the graphics card and any other card, I/O card that you wanted to directly connect with high performance, and they connected it to the CPU memory bus again. And because the top of the line CPU at the time was the 486 CPU running at 33 megahertz, that was the bus standard for the VL local bus. And the problem, of course, with doing that is that they married it to the 486 CPU bus protocol, and when other CPUs came out, particularly the Pentium, it used a different bus protocol, and the VL bus was no longer an option. It simply didn't work. Later on, IBM tried to create a future-proof and CPU-independent alternative to the ISA bus as part of their MCA microchannel architecture design. And we'll talk about that bus and the VL bus in some future slides. This slide shows the original IBM PC-80 motherboard from 1984. This is the board that uses a 8286 CPU. And you can here see the two different slots. This is the legacy original PC slot, and this is the extended, you see the extension here, connector for the actual ISA slot, which is part of the ISA standard from 1984. So technically this is the only true ISA slot, but we refer to both as ISA slots and therefore ISA boards. So in this slide behind me here, you see the pinout of the ISA bus connector. This is the hold connector for the that is spec'd as part of the 286 computer, and this part here is the original PC connector, the 8-bit. You have 8 data bits on this connector, and you have another 8 on this. So in total, you have 16 for the whole interface.
PCI Express. Einige werden sich jetzt fragen, warum erklärt ihr mir eine 10 Jahre alte Schnittstelle? Aber Tatsache ist, PCI Express war lange Zeit für viele Leute einfach nur der Slot, wo man die Grafikkarte reinsteckt. Und die Details haben eigentlich gar nicht so interessiert. Erst in den letzten Jahren, wo immer mehr PCI Express Geräte und Erweiterungsmöglichkeiten auf den Mainboards Einzug halten, wird es eigentlich immer wichtiger, was diese Schnittstelle eigentlich alles kann und macht. Und auch meine Mainboard-Reviews konzentrieren sich immer mehr darauf, welche Erweiterungsmöglichkeiten eigentlich über PCI Express geboten werden. Und viele Leser haben mich gefragt, was ist das eigentlich? Was ist eine PCI Express LAN? Was kann die? Wofür ist die da? Und deswegen versuche ich das heute nochmal ein bisschen zusammenzufassen. Erstmal als Kontrastprogramm, was PCI Express nicht ist, nämlich der Vorgänger PCI. Wir hatten bis vor 10 Jahren die primäre Schnittstelle für Erweiterungskarten. Seitdem versucht PCI Express das abzulösen, klappt aber immer noch nicht so ganz. Selbst für Skylake erscheinen wieder Mainboards, wo auch PCI drauf ist. Aber ich habe hier mal ein ganz altes mitgebracht, um das so ein bisschen zu verdeutlichen. Die Besonderheit bei PCI war, alle Slots hingen an einem gemeinsamen Bus und es waren auch relativ große Slots mit vielen parallelen Datenleitungen. Das heißt, wir haben hier 32 Datenleitungen, die gehen einmal komplett durch und jeder Slot hängt dran. Das war recht praktisch, weil man die Leistung auf beliebige Karten verteilen konnte. Nur war die Leistung irgendwann zu wenig und man konnte sie kaum steigern. Denn mit 32 parallelen Datenleitungen hat man das Problem, wenn die nicht alle genau gleich lang sind, genau gleich arbeiten, kommt am Ende nur noch Blödsinn raus. Die einzelnen Bits kommen nicht zum gleichen Zeitpunkt an über die vielen unterschiedlichen Wege und das Ganze macht das Mainboard-Layout sehr komplex. Deswegen hat man für den Nachfolger PCI Express ein komplett anderes Modell gewählt. In Hardware haben die beiden eigentlich gar nichts gemeinsam. Der Name ist zwar noch gleich und auch das Ansprechverhalten der Karten durch das Betriebssystem ist gleich. Das heißt, man musste Windows nicht umgestalten, um die neue Schnittstelle einzuführen. Aber mechanisch und elektrisch sind die komplett anders aufgebaut. Man sieht das hier schon so, die klassischen PCI Express Slots, die meisten werden sie zumindest kennen, gibt es zum Beispiel in unterschiedlichen Längen. Und das ist schon erst ein Hinweis darauf für das Grundkonzept, denn PCI Express arbeitet mit sogenannten Lanes. Wir haben nicht mehr einen Bus, wo ganz viele Datenleitungen versuchen parallel zu arbeiten, sondern wir haben eine einzelne Einheit, die nur aus einer Datenleitung vom PCI-Controller, zum Beispiel in der CPU, zum PCI-Endgerät, zum Beispiel auf der Steckkarte führt und eine zweite Datenleitung für den Datenverkehr in Gegenrichtung. Und diese beiden Leitungen arbeiten als eine Einheit, haben ihr eigenes Taktsignal und können sich nicht irgendwie gegenseitig stören, weil es ist halt nur eine Datenleitung, auf die die Daten hintereinander sequenziell kommen, statt dass man parallel mehrere Datenleitungen koordinieren muss. Wenn man bei PCI Express die Bandbreite aber über das Maß einer Lane hinaus steigern möchte, hat man auch die Möglichkeit, mehrere Lanes in einem Slot zusammenzufassen. Das heißt, wir haben hier zum Beispiel einen X4-Slot und hier einen X16-Slot, das ist der, den man typischerweise für Grafikkarten nutzt. Der ist logischerweise bei gleichem PCI Express Standard 16 mal so schnell wie der X1. Und auch hier ist das nicht etwa eine große parallele Schnittstelle, sondern wir haben hier wirklich 16 unabhängige Systeme zur Datenübertragung. Und wenn das eine mal ein bisschen anders arbeitet als die anderen, dann stört das nicht. Denn die Daten werden über jedes einzelne Lane als Pakete übertragen und erst die Pakete werden am Ende in der GPU wieder zusammengesetzt. Und dabei ist eigentlich vollkommen unabhängig, in welcher Reihenfolge die eingetroffen sind, solange sie jetzt nicht, ich sag mal, wirklich lange verzögert und zu spät kommen. Aber die genaue Timing ist nicht mehr wichtig und man hat somit wesentlich mehr Möglichkeiten, die Leiterbahn über das Mainboard zu führen. Die können auch mal ein bisschen unterschiedlich lang sein. Ein weiterer Vorteil dieser Lane-Bauweise sieht man schon, wenn man sich die Slots mal genauer anguckt. Und zwar fängt jeder PCI Express Slot ähnlich an. Wir haben hier diese etwas längere Kerbe, dann beginnt die kurze. Bei den großen Slots geht es dann halt einfach länger weiter. Aber der erste Abschnitt eines X16-Slots sieht genauso aus wie der X1-Slot. Und das ist auch absichtlich, denn man kann jede PCI Express-Karte auch in größeren Slots betreiben. Ich kann hier zum Beispiel meine X1-Karte auch nehmen und sie in den X16 stecken, wenn ich einen davon zu viel hatte. Und sie wird da genauso arbeiten wie in einem X1-Slot. Wesentlich flexibler, was die Nutzung von Slots also angeht. Es geht sogar umgekehrt. Einige Mainboard-Hersteller verbauen PCI Express Slots, die nach hinten hin offen sind. Das heißt, ich kann jetzt hier in einen mechanischen X4-Slot eine X16-Grafikkarte reinstecken. Und wie man vielleicht sieht, die Kontaktleiste der Grafikkarte ragt einfach nach hinten aus dem Slot heraus. Das heißt, sie kann 12 von ihren 16 Lanes gar nicht nutzen. Aber mit den ersten 4 wird sie genauso arbeiten wie sonst auch. Ein bisschen langsamer. Aber das Protokoll sieht vor, dass die Karten auch mit weniger Lanes zurechtkommen müssen. Also alles einfach und flexibel und super toll mit PCI Express. Dann würde ich jetzt garantiert kein Video drüber machen. Es kommen nämlich weitere Komplikationen hinzu. Genauso wie ich eine X16-Karte in einem X4-Slot betreiben kann, wenn sie mechanisch da reinpasst, oder eine X1-Karte in einem X16-Slot, spricht nämlich auch gar nichts dagegen, einen mechanischen X16-Slot mit deutlich weniger als 16 Lanes anzubinden. Und da kommen wir jetzt nämlich zu dem Dauerthema PCI Express Sharing und Umleitung von Lanes, um an irgendeiner anderen Stelle andere Hardware anzubinden. Ein aktuelles Beispiel habe ich euch mal mitgebracht. Ein brandneues Skylake Mainboard. Wer die Berichterstattung über die CPUs mitverfolgt hat, wird gehört haben, dass in der CPU ein PCI Express 3.0 Controller mit 16 Lanes sitzt. Wer sich dieses Board nun genauer anguckt, dem fallen 3 optisch hervorgehobene mechanische X16-Slots auf und die sind entsprechend der Folgen tatsächlich auch alle über die CPU angebunden. Wenn man jetzt kurz nachrechnet, 3x16 auf 1x16, das geht nicht auf. Und das ist typisch für moderne Mainboards. Und man kann immer sehr schön daran notieren, wenn man irgendwo diese rechteckigen Chips sieht, in dieser typischen, sehr regelmäßigen Anordnung, dann hat man quasi immer PCI Express Sharing auf dem Board. In diesem Fall sind 8 der 16 CPU-Lanes permanent mit der ersten Hälfte des obersten Slots verbunden. Die anderen 8 Lanes gehen aber erstmal zu diesen, ich nenne sie immer PCI Express Splitter. Und die haben die Möglichkeit, zwei ankommende Lanes je Chip in 2 verschiedene Richtungen weiterzuleiten. Entweder ebenfalls zum ersten Slot, dann erhält er alle 16 Lanes, oder aber sie leiten die 8 Lanes, die zu diesen 4 insgesamt gehen, zum zweiten Slot weiter. Dann haben wir hier also hier nur 8, aber hier auch 8 Lanes. Normalerweise kriegt der zweite gar keine. Der Trick dabei ist, das Ganze wird einmal beim Einschalten des Systems festgelegt. Das heißt, sobald ich eine Karte in diesem Slot hier montiert habe, selbst wenn sie gerade gar nichts zu tun hat, kriegt die erste Karte, meistens die Grafikkarte, immer nur 8 Lanes ab. In diesem Fall geht es sogar noch weiter. Sitzen nochmal 2 dieser schönen Chips. Die können von den 8 Lanes, die in diesem Slot weitergeleitet wurden, 4 Stück nehmen und noch einmal an diesen weiterleiten. Das heißt, obwohl dieses Mainboard garantiert von einigen Händlern mit 3x16 beworben wird, ist es eigentlich ein 8-4-4-Board. Einen kleinen Sonderfall des CPU-Lane-Sharings möchte ich an der Stelle auch erwähnen, weil er gerade auf besonders teuren Board anzutreffen ist. Und zwar gibt es nämlich einen Trick, sogenannte PCI Express Switch. Manchmal werden auch diese Umschalter, die ich gerade schon vorgestellt habe, als Switch bezeichnet. Der Begriff Schalter ist da im Englischen leider nicht ganz deutlich. Was ich hier meine, ist ein Switch im gleichen Sinne, wie es auch zum Beispiel bei Netzwerk-Switch verwendet wird. Das sind spezielle Chips, die nehmen die Lanes, die zum Beispiel von der CPU kommen, und bereiten diese intern auf. Das heißt, eigentlich ist der Chip mit 16 Lanes in diesem Fall an die CPU angebunden. Dieser Chip hat seinerseits 32 weitere Lanes, mit denen er andere Geräte anbinden kann. Bei derartigen Boards ist es also tatsächlich möglich, dass 2 Grafikkarten parallel mit 16 Lanes arbeiten und die können auch beide mit voller 16-Lane-Geschwindigkeit mit der CPU kommunizieren, nur halt nicht unbedingt zeitgleich. Es sei denn, es müssen zufällig genau die gleichen Daten von der CPU zu den Grafikkarten übertragen werden. Alternativ können sie auch untereinander mit der vollen Geschwindigkeit kommunizieren, ohne dass die CPU überhaupt belastet wird. Derartige Switches sind also eine Möglichkeit, die Leistung durchaus ein bisschen über das zu steigern, was die CPU selbst kann, und werden deswegen vor allem auf sehr teure Mainboards verbaut. Ich zeige das auch nochmal auf der Rückseite. Das kann man hier mit etwas Glück erkennen. Man hat hier also wirklich die Leiterbahnen, die von der CPU kommen. Die enden hier in diesem Bereich. Und von hier aus gehen deutlich mehr Leiterbahnen wieder los und zu den Lötkontakten der einzelnen Slots. Die gerade angesprochene Verteilung der CPU-Lanes mag jetzt einigen Leuten schon komplex erscheinen, aber eigentlich ist es relativ übersichtlich. Es gibt auf den meisten Boards die Möglichkeit, Lanes an weitere Slots umzuleiten. Auf einigen Boards gibt es halt noch die beschriebenen PCI Express Switch, die für effektiv mehr Lanes seitens der Endgeräte sorgen, als die CPU eigentlich bereitstellen kann. Das kann man in den Spezifikationen meistens ganz gut nachlesen. Unübersichtlich wird es nur bei der Sockel 2011 V3-Plattform, schlichtweg weil Intel da eine CPU anbietet, die weniger Lanes zur Verfügung stellt als die Top-Modelle der Plattform. Und das sorgt halt dafür, dass es alle Bandbreitenangaben in zweifacher Ausführung gibt, je nachdem, welche Chip man verbaut hat. Wirklich kompliziert wird es aber bei der zweiten Quelle von PCI Express Lanes auf modernen Mainboards. Und zwar hat nämlich auch der Chipsatz, der heutzutage nur noch aus einem Chip besteht und bei Intel PCI heißt, bei AMD FCH, ein PCI Express Controller eingebaut. Und der wird nicht nur genutzt, um Erweiterungsslots anzubinden, sondern auch diverse Zusatzcontroller. Zusätzliche SATA-Ports, USB 3.1, zum Teil auch zusätzliche 3.0 Ports, wie gehabt schon X1-Slots, X4-Slots und manchmal auch noch diverse weitere Sachen. Natürlich bei der neuen Generation sehr beliebt der M2-Port für schnelle SSDs. Da gibt es vielfältige Möglichkeiten. Auch Netzwerk oder einige Audiochips werden über PCI Express angebunden. Es sind also sehr, sehr viele Endgeräte, die in Frage kommen. Und diese Chipsätze haben auch nicht wirklich viele Lanes.
The computer currently has one IDE hard drive. This is connected to the primary IDE controller. It also has a single optical drive which is connected to the secondary IDE controller. I'm going to be adding a second IDE hard drive, and I'm going to add it as a slave device to the primary controller. I will be removing the original hard drive so I can show you what the hard drive looks like, and then also so we can reconfigure the jumpers. First I'll begin by removing the power lead, gripped onto the Molex connector, and then I pull it out of the device. Then I remove the ribbon cable. I grab the ribbon cable close to the connector and then pull straight out from the device. Each computer case manufacturer holds hard drives into the case differently. Some computer cases use a quick release rails. These will snap onto the hard drive so they slide into the case. Others will have a plastic or a metal removable cage that holds the hard drive in. This one happens to have a fixed cage. This is welded right to the case, and then it uses screws to hold the drive in place. I'll remove these screws so then I can slide the drive out of the case. With the screws removed, I can carefully move all the components out of the way and then slide the drive out of the case. Here's the IDE drive that I removed from the computer. Here we have the 4-pin Molex power connector. We have our 40-pin IDE controller. Has a keyed notch here so our data cable can only fit in one direction. And then our IDE device has jumper settings. Somewhere on the IDE drive there will be a legend or some indicators to indicate which jumper setting will specify the device as a slave or a master device or a cable select device. In this case, if we remove all jumpers, that would be a slave device. If we set the jumper to the far right, that would be a master or single drive. Or if we set it on the third jumper, that will indicate or enable the cable select feature. This device is going to be our master device. So we're going to set it as the far right jumper. So this white jumper right here is already in the proper location. So this device will be the master device. We're going to install this on the primary controller. This device is going to be our slave hard drive. We're going to add this to the primary controller. This device doesn't happen to have a legend on top, but if I turn it over, the bottom jumper settings are listed right on the board. So here we have CS. If we were going to have a cable select device, we would use the first jumper. If we were going to specify this as a slave device, we would use the second jumper, and then the master device would be the third jumper. In this case, this is going to be our slave device. We will move it over to the second jumper. So this device is now configured as our slave device. IDE devices support one of two settings. We can either set all devices as the master or slave device, or we can set both devices as cable select. If we use cable select technology, we're going to have to use a cable select supported cable. Here's an example of a cable select supported cable. A couple of items on a cable select cable. One of them will have a little notch out of it. So in this case, we have one of the wires has been punched out. We also have markers on the connectors to indicate which connector goes to which device. In this case, this one says sys board, so this plugs into the motherboard. The connector at the end of this cable supports drive 0, so we would put our drive 0 or our master device on the end of the cable. And then drive 1 or our slave device would go on the center connector. So if we're using cable select, we have to use a cable select cable. Some IDE cables like this one are what are called 40-wire cables. So there's 40 wires and a 40-pin connector. These are used for optical drives and legacy hard drives that only support ATA 33 or less speeds. Newer drives that are ATA 66, 100, or 133 need to use an 80-wire cable. These still have a 40-pin connector, but they have twice as many wires to support faster speeds. You can use a 40-pin cable with an ATA 66, 100, or 133 device, but it won't run at the fastest speed. So it's recommended to use these cables, the 40-wire cables, only for optical drives, and the 80-wire cable for any newer hard drives. Remove the ribbon cables from the motherboard so we can get a good look at them. Under each of these IDE controllers we can see that this one says primary and this one says secondary. So we're going to connect our master and slave hard drives to the primary controller, and then our single optical drive will be on its own cable connected to the secondary controller. Whenever possible, you should separate hard drives and optical drives on separate controllers. In this case, we're going to put our hard drives on the primary controller and our optical drive on the secondary controller. You should also put your bootable drive that holds the operating system, you should configure that as the master device on the primary chain, and then any other hard drives or secondary hard drives should be configured as the slave device on the primary chain. Currently, our single optical drive is connected to the secondary controller. This cable is connected to our primary controller. This is what will attach our master and our slave hard drive. This is going to be our master device. We've got the jumper set correctly, so this is the master. Carefully insert this into the computer case and then install the case screws to hold it in place. Installed and fastened the case screws. Now I can connect the data ribbon cable. Generally you want the master device hooked to the end connector on the ribbon cable. This is our master device, so I'll connect the ribbon cable, and at this time I can also connect the power connector. Now I can install our slave device. This is our slave device. We've got the jumper settings set as slave, so I can carefully slide this into the computer case and then fasten the case screws. The hard drive screws are fastened. Now I can connect the secondary connector to our slave device. And then the second power connector. Here's a close-up to our setup. Here's our master device connected to the end of the cable. We have power connected, and then the secondary connector is connected to our slave device. This one also has power, and this cable is connected to our primary controller. With the hard drives installed, I can connect my monitor, keyboard, and mouse, power up the computer, and make sure that both drives are detected. Press the power button and boot the computer. As it boots, I can look at the BIOS splash screen, see if there's any indication that it found any devices. Press the pause break key to pause it. Here it indicates that it found a primary master device. It also found a primary slave device, and then a secondary master device. The delete key to enter the CMOS setup utility. Then I'll go into the standard CMOS features, and here we can see our current IDE setup. You can see our primary master device was auto-detected. It's a 40,000 megabyte or a 40 gig drive. Our primary slave device was auto-detected. It's a 19,996 megabyte or a 20 gigabyte hard drive. And then our IDE secondary master is an MSI CDRW. That's our optical drive. Looking at both the BIOS and the CMOS, it appears that the jumpers were set correctly and all devices were properly identified. So from here we could save our settings, the computer would restart, and then we could go into whatever operating system we're using, and now we would partition and format our hard drive to be able to use it.
The abbreviation SCSI is pronounced SCSI, and this stands for Small Computer Systems Interface. It was a method of connecting storage devices in, at that time, were small computer systems or personal computers, and it was one of the very first ways that we had standardized storage on our computer systems. We were able to do quite a bit with this. We could string a number of devices together. They could be hard drives, they could be optical storage devices, and we could put up to 16 devices on one of these SCSI chains using a single cable and a single SCSI controller. So you were able to just put one interface in your computer and simply hang off the back of that interface 16 different devices. Through the years, there have been a number of different kinds of SCSI formats. You may see it called fast SCSI, ultra SCSI, there's ultra wide SCSI, there's ultra 2 SCSI, and so on. All of these formats tend to be backwards compatible, but the best possible performance you're going to be would be to get a storage device and a controller that were using the same type of SCSI interface. Before USB came along, SCSI was really the standard for connecting our peripherals together. We would plug in printers, scanners, tape drives, CD-ROM drives, anything that needed an external connection. SCSI was the format that we were using. On these SCSI buses, we had different sizes. We had a narrow bus SCSI. Some SCSI was a wide bus. The narrow bus could plug in 8 devices that we could string onto an individual controller. The wide bus allowed us to have 16 different devices on a single controller. The part of SCSI that really makes it powerful is that the interface and the communication itself is very, very intelligent. It's very powerful. We're able to do a lot of different communication over that SCSI bus, and it was very simple to plug in. Even though we were able to control so many diverse kinds of devices, it was a single type of interface. We assign a number to it, and now we've got a SCSI connection on our computer. SCSI has been around for a very, very long time. But even today, especially in large server farms, we see SCSI interfaces for hard drive controllers, and especially on virtualized environments, we see a lot of SCSI being used. Even though it's not a physical SCSI connection, we're still using that SCSI standard of protocols to communicate over these virtualized systems. One particular piece of SCSI that was very important, especially early on in SCSI, was the termination. You could plug many devices in, but the last device had to have what we called a terminator on the end of the chain. That way, the SCSI communication knew exactly where the signal ended. Without a terminator, none of these devices would be able to operate properly. The newer SCSI devices tend to have these terminators built into the device, and you can enable or disable the terminator just by clicking a button. But the older devices needed a physical terminator that you would connect to the interface that was on back of the SCSI device. There are many different types of interfaces that you'll see for SCSI. They've changed quite a bit through the years. Here's an example of one. You can see this one happens to be an Ultra 3 SCSI connection, and you can see a PATA connection right next to it. They're almost the same size. The SCSI might be a little bit shorter. This is a view from above. If we were to look at it from the side, you can see the interface connector is a little bit different than the PATA or the SATA connections that we've used before. This SCSI connection has quite a number of pins associated with it. The cable that we would use to connect this would be something like this, where we would plug into the motherboard, and then there might be many different connections on that same cable where we could use all of these different SCSI devices and plug them all in at the same time. If we were to look closer, you can really see a lot of different pins being used. And on this particular SCSI connection, it was a higher bandwidth, so it needed a lot more pins to be able to communicate. But it may not be this type of connection that you would see with SCSI. Because they've changed so much through the years, you might see a DB25 connection that looks like a serial, or maybe even an older parallel connection. They all look very similar, but these are actually SCSI connections. You have to look very carefully to see the differences. Some connections are very clear that they're SCSI. This high density 50 pin connection has locks on the side of it that connect in. That's very, very exclusive to SCSI. And some of these higher density connections as well really make you see that very quickly that's a SCSI connection. There's nothing else that looks quite like those connectors. When you're physically connecting SCSI devices to the SCSI cable that you have, whether they are inside of a computer or outside of a computer, you have to give each one of them a completely unique number. This is called a SCSI ID. So on that single bus, on that single connection coming out of an interface of a computer, we would provide different IDs. For instance, if this was your boot disk, maybe we'll give that SCSI ID 0. If there's a floppy disk or a scanner or an optical device, we might assign that a number 2. If there's a CD-ROM, we might assign that with a SCSI ID of 3. There's also a concept within SCSI connections called a logical unit. So within each physical SCSI ID on that interface, you might have logical units inside of this. This was very common to see if you were plugging in an external SCSI storage device that had multiple hard drives inside of it. You would give the storage device itself a SCSI ID, and then there would be logical units assigned to the individual drives within that single physical device. You also see this quite a bit when you're working with virtualized systems. As I mentioned earlier, the signal that is at the very end of the SCSI bus has to be terminated. There might be a physical terminator, or it might be a termination functionality that's built into the hardware itself. If you ever see what we call SCSI attached devices that are serial attached SCSI, they don't have jumpers, they don't have terminators, they don't have settings. A lot of the more modern storage devices that we are plugging in over something called serial attached SCSI are completely automated in the way that they configure themselves on that SCSI bus. Here's an example of a legacy SCSI device. I think this is an optical device, but it could be a hard drive, it could be a scanner, it could be anything else. Generally, we see two different types of connectors on the back of the device. One of them generally is the connection going in. You can see it written on the back of the device, where we would plug in the in connection from our computer. If we had additional SCSI devices, we would use this out connection to keep the string going, to keep that daisy chain going throughout the connection. If this was the end of the line, if this really was the last device in this SCSI chain, this is where we would plug in the terminator. If this was a device that had the termination built in, there would probably be a connector on this device, or a button you could push to say this was the terminating place. And you can also see the SCSI ID number built right into this as well. There's little buttons that would allow you to change that SCSI ID. So when this device plugged in and communicated across the SCSI bus, everyone know that this device was SCSI ID number 6. Once you have everything plugged in, it looks a little like this, where you have a SCSI controller that might be ID 0. Here's SCSI ID 1. That's a hard disk. Here's another hard disk, and they're all chained together with different SCSI IDs. And at the end of the chain is a terminator. Usually these terminators even have a little light so you can see that they are active. Here's a picture of what a SCSI terminator might look like, so you can look at the back of your devices and see if you have one of those. That term daisy chain actually came from this idea of taking daisies and connecting them to each other, and you could wear them as bracelets or wear them on your head. And that same daisy chaining was how we came up with this idea of plugging in all of these devices one to the other to create that chain of devices. The back of the SCSI drive looks very similar to the back of any other hard drive. It's just using a very specialized SCSI connection on the back. Usually you have jumpers that can help you designate what the SCSI ID of this drive happens to be. And here's traditional power that you might find so that that drive can be powered up on the inside of your computer. If this was an external device, then you have external power. You usually have options for setting your SCSI IDs that we saw on the SCSI device earlier, and the interfaces for going in and out of that SCSI connection. The connection of the SCSI device on your motherboard looks very similar to PATA in that we've got a connection on the motherboard and multiple interfaces on SCSI. But of course, with PATA, we are limited to 2 individual devices, whereas with SCSI, especially the wide bus SCSI, I can connect up to 16 devices, and you would simply find the closest connector to you and plug it in. It doesn't matter where along this particular cable we plug in our SCSI device. The determination of how this device communicates is associated with the ID that you assign to the SCSI device. So you simply plug into the closest connector to you and plug in all of your different SCSI devices. Make sure they have different SCSI IDs, and your SCSI communication is now complete. Once you follow those rules, SCSI is very simple to get running, and it's going to provide you with a lot of flexibility to plug in multiple storage devices. If you're working with a relatively new computer, then it most likely is using SATA connections to plug in the storage devices inside of that computer. Here's an example of one of those. This is a 256 gig solid state drive that is using SATA connections to be able to communicate. We'll look closer at what that might look like. SATA stands for Serial AT Attachment, that AT attachment being that older AT computer, one of the original style computers, and we've kept the terminology through the years. Although the original computers are well beyond us, we have this serial AT attachment to have some comparison back to the older parallel AT attachment, or PATA. We have different standards for SATA. One of the original SATA versions was version 1.0. It ran at 1.5 gigabits per second. There's also another standard, which is the SATA revision 2.0, which is running at 3.0 gigabits per second. The latest SATA standard goes even faster than that. That's SATA revision 3.0 that runs at 6 gigabits per second. One thing you have to watch for is occasionally you will see people abbreviate 3 gigabits per second as 3G. We can sometimes confuse 3G with third generation. That's not really the case. I've been very careful here to show you SATA revision 1, SATA revision 2, and SATA revision 3, and then the speeds of those being 1.5 gigabits per second, 3 gigabits per second, and 6 gigabits per second. So if you're looking at standards for SATA, make sure you don't confuse any of that terminology. It can become confusing when you're dealing with different versions and different speeds, but as long as you synchronize those up, you shouldn't have a problem. One of the advantages that SATA brings to the table is that the connections are much smaller on the motherboard. You can see one of the older IDE or PATA connections on this motherboard, and this motherboard also has SATA connections, 1, 2, 3, 4, 5, 6 different SATA connections. If you were to look at these cables side by side, you'd really see the difference. PATA uses these larger ribbon connections. Here's the SATA connections, a much smaller connector on the motherboard and a much smaller cable that's being used to the storage device. So for the purposes of managing cables inside of your computer and making sure that the airflow is maintained through your computer, SATA has some distinct advantages. This is the back of a SATA drive, very similar to the PATA in that your interfaces are on this side. It's actually this very small interface is the SATA data connection. This larger interface is actually the power for SATA. You've also got these jumpers, and then you have an older traditional power connection. This drive was built for a computer that may be transitioning between PATA and SATA, and they gave you the option you could either plug in with the newer SATA power, or you could plug in with the older 4-pin Molex connector onto this drive. You would only choose one of those. You wouldn't need to plug both of those in. One of the advantages with SATA, however, is there's the capability on a number of drives to do hot swapping. You could unplug this drive while your system was powered up and plug it back in. That would be something you would not commonly do, and you would certainly want to take proper precautions when you were doing something like that, but it is part of the SATA standard. If we were to look at the top of the drive itself, it would give us that documentation of what we just saw with the power on one side, our serial connection, which is the data connection to our motherboard, the jumpers that are on the side, and there's a legacy power connection built in right into the documentation on the top of the drive. If your power supply had some of the newer SATA connections, you would simply plug the power connection into the SATA power, and you would plug your data cable into the SATA connector on the drive. If you have an older power supply, then you would plug it in very much like this picture shows, where you still have the same data connection, but you would use this legacy Molex power connector to make sure the drive was operational.